Every time you turn on a light, flush a toilet, or board a train, you're relying on a system you've probably never heard of. It's not powered by Silicon Valley, and it wasn't built for a digital world. Yet without it, modern civilization would collapse in days. This is the invisible technology that runs the world, and right now, it's under attack.
The U.S. is vulnerable to a large-scale and devastating cyber attack. Panetta said that foreign computer hackers are targeting systems that operate chemical, electricity, and water plants.
Ellis County Sheriff says someone tried to poison the water supply in Oldsmar through a computer hack.
The hackers zeroed in on the Wolf Creek nuclear plant in Kansas.
The government say our vital infrastructure is increasingly under threat from cyber attack.
I'm talking about operational technology, or OT for short. For decades, the idea of hackers causing physical damage felt like science fiction. Homes were safe, infrastructure was untouchable, until a German engineer named Ralph Langner found something no one had ever seen before. A piece of malware that didn't steal data, it broke machines. OT malware didn't exist before Stuxnet. Stuxnet wasn't just a hack, it was the world's first digital weapon. It was designed to sabotage a nation's infrastructure by physically damaging Iran's nuclear program.
Warfare, cyber warfare against physical infrastructure is absolutely feasible. Okay? Whoever did this showed that it can be done again.
It marked the beginning of a new era of cyber warfare that had physical consequences.
If somehow attackers could distribute a payload to hundreds of millions of computers in a very short period of time, and then cause that payload to damage those devices in such a way that it's not just about fixing the software, but they actually hurt the hardware, which is possible in many computers. You could have an infrastructural outage that would take months to repair, because you'd have to literally get new hardware, have people, technicians go from computer to computer.
Before this, computer hacking was largely viewed as a nuisance, perpetrated by pranksters, or espionage focused on stealing information rather than a tool for causing physical destruction. While theoretical at the time, the idea of cyber attacks damaging industrial infrastructure was not considered an immediate, tangible reality. What Stuxnet revealed wasn't just a flaw in one facility, it exposed a weakness in the everyday systems that keep all our lives running. And suddenly, this wasn't just a story about geopolitics or nuclear programs, it became a story about all of us. You may think that you never interact with OT, that it's some distant, technical world that has nothing to do with you. But OT is woven into every part of your daily life. It pumps the water you drink, powers the electrical grid that lights your home, moves the buses and trains you ride, and even keeps your local nuclear power stations chugging along. OT isn't out there, it's everywhere, quietly holding society together, and that's exactly why it matters. Every device we rely on, every smart convenience, sits on top of an aging foundation of operational technology. And much of that foundation is still running on software written in the 1980s. These systems were never meant to touch the internet. For decades, that isolation kept them safe, until suddenly it didn't. To keep up with the modern day and evolving technology, advancements in industry have pushed organizations to make OT more autonomous. This removes the element of human error. Increasing the efficiency has increased shareholder value, and making everything interconnected has saved government departments and private businesses money. But it's also created a way in. And to understand why connecting these old systems created so many new risks, we need to look at how OT is built at its core. While IT manages data, OT controls the physical world, and because of that difference, they both live and work in different environments. To understand why OT is so vulnerable, you need to understand how it actually works. At the heart of most industrial systems are PLCs, programmable logic controllers. These are rugged computers designed to run one task, endlessly, without failing. They read sensors, make decisions, and control actuators. A PLC might open a valve, start a pump, or shut down a turbine if temperatures rise too high. Above the PLCs sits the SCADA, which stands for Supervisory Control and Data Acquisition. This is the interface operators use to monitor entire facilities. It's like OT's operating system. It provides a central platform that manages hardware, handles data, and runs software applications to control machinery. SCADA shows temperatures, pressures, flow rates, and alarms. It's the digital window into a physical world. Larger facilities use a DCS, distributed control systems, networks of controllers working together to manage complex processes, like chemical plants, refineries. These systems prioritize availability above everything else. In OT, uptime is sacred. A few minutes of downtime can cost millions or put lives at risk. So for decades, the rule was simple. If it works, don't touch it. And for a long time, the air gap, the simple fact these systems weren't connected to the internet, kept attackers out. That mindset kept OT stable, but it also froze it in time. But as the world began to modernize, something else happened. The once clear line between OT and IT began to blur. For decades, the difference was obvious. IT lived in offices, email servers, databases, websites, business apps. OT lived in the physical world, pumps, turbines, conveyor belts, generators. One dealt with information, the other dealt with reality. But when OT systems finally crept online, these two worlds started to merge. And today, in many places, it's almost impossible to tell where OT ends and IT begins. Take autonomous vehicles. They're packed with sensors, motors, braking systems, all classic OT. But they also rely on cloud-based navigation, machine learning models, over-the-air updates, and real-time data systems. Pure IT. A glitch in the software now can cause a failure in the hardware. A cyber attack can become a physical crash.
Oh my god, 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 oh my god!
The same is true for smart grids, where traditional power equipment is now controlled by digital meters, remote management tools, and AI-driven load balancing, or IoT-enabled factories where robotic arms, temperature sensors, and conveyor systems are all tied into a corporate network, sometimes even connected to the public internet. Even server farms, which seem like pure IT, rely on OT systems to survive. Cooling pumps, backup generators, fire suppression systems, and power distribution units. If these OT components fail, the IT world collapses with them. This convergence has created a new kind of infrastructure, hybrid systems, part machine, part computer network. And when OT becomes IT, it inherits IT's weaknesses. Remote access, misconfigurations, exposed interfaces, and the constant threat of cyber intrusion. Which brings us to the heart of the problem. To understand why these blended systems are so vulnerable, we need to understand how an OT actually works under the surface. OT didn't start digital. In the 1960s, industrial systems were electromechanical, relays, switches, and analog gauges. In the 70s and 80s, PLCs replaced physical relays, but they were still isolated. In the 90s, serial networks connected machines but only inside the facility, and by the 2000s, Ethernet had crept in. By 2010s, remote access became normal, often added quickly, cheaply, and without security. The moment OT touched the internet, everything changed. Systems designed to run untouched for decades were suddenly exposed to the outside world, and attackers had noticed. But there was another problem, one hiding in plain sight. OT systems are so old and so brittle that even malware from the early 2000s can still break them. Code written for Windows XP The kind of virus modern security tools would erase without a second thought can still knock out critical machines running outdated software. And the danger doesn't stop there. These old pieces of malware were never designed with industrial control systems in mind. So when they hit OT, the effects are unpredictable. A simple worm meant to annoy office computers can accidentally shut down pumps, overload sensors, or crash control systems. In IT, that malware is a relic. In OT, it can still cause millions in damages or bring entire facilities to a halt. December 23rd, 2015, Western Ukraine. It's 2 days before Christmas. It's freezing, and inside a power distribution centre, an operator is finishing his shift. Suddenly, his mouse starts to move. He isn't touching it, he watches, powerless as the cursor slides across the screen with purpose. It navigates to the control software. It hovers over a breaker, and then it clicks. In an instant, a city goes dark, then another and another. The operator tries to grab the mouse to take back control, but he's been locked out, a spectator to his own disaster. This wasn't a glitch. It was the first time in human history that a line of code physically turned out the lights for an entire nation. But they weren't done. To ensure maximum chaos, they launched a denial of service attack on the company's phone lines, flooding them with thousands of fake calls so real customers couldn't even report the blackout. And as a final screw you, they wiped the servers clean and turned the control center's computers into useless bricks of plastic and silicon. This was the work of Sandworm, a Russian-linked hacking unit that treated a civilian power grid like a laboratory. Ukraine was the test, and the rest of the world was a target. They proved that in modern warfare, you don't need to drop a bomb to disable a city. You just need to find the right PLC. So if we know that our power, water and heat, our nation's critical national infrastructure, is all targets for foreign military, why has this not been fixed? The answer is a brutal reality of the modern world. We are fighting a 21st century war with 20th century tools. In the IT world, you can patch a server in minutes, but in OT, fixing it means shutting down the lifeblood of a city. Because these systems were built in the 70s and 80s, they don't have firewalls. Some don't even have the ability to authenticate a user with a password. Their backups aren't kept in a cloud or a secondary server farm. They're kept on a floppy disk in the desk drawer. But it's not just about old tech, it's about how we're forced to evolve. Walk into a typical factory or a local water treatment plant, and you won't find a sleek unified system. Instead, you'll find a Frankenstein's monster of technology. You'll have machines from the 1980s that were originally designed to output data to a physical dot matrix printer. They were never meant to talk to anything else. But over the years, we've bolted on layers of modern convenience. We've taken that 40-year-old machine and wired it into a laptop from the 2010s so an operator can monitor it from his desk. Then, we connect that laptop to a modern server so the data can be seen at the head office. Finally, we plugged that server into the internet so a contractor could troubleshoot it from home. The air gap, that physical disconnect that we use to keep these machines safe, is gone. It didn't disappear overnight. It was bled away by 1,000 convenient business decisions. We've turned isolated simple tunes into accidental gateways for foreign military. The issue isn't just the age of the equipment, it's the erosion of the expertise required to manage it. Most of these systems were bespoke, custom built by engineers decades ago to suit the specific requirements of a single facility. As that generation reaches retirement, they take years of specialised knowledge with them. Today's technicians are often tasked with maintaining systems where the original manuals are gone missing, and the companies that manufactured the components have long since gone out of business. In this environment, a standard security patch becomes a significant operational risk. There is no test environment for a 30-year-old water pump. If an update causes a software conflict with a legacy controller, it doesn't just crash a computer, it can halt an entire production line. For many operators, the most logical decision is to avoid updates entirely to maintain uptime. From an executive perspective, the choice to leave these systems alone isn't about being lazy, it's a cold, calculated risk. If you're a CEO, you're looking at a nightmare scenario. On one hand, you have a theoretical threat from a group like Sandworm. On the other hand, you have the guaranteed cost of an upgrade. Replacing the foundation of a plant costs tens of millions, but the downtime is what kills a business. Shutting down a major refinery or a city's power distribution for weeks just to swap out the brain of a machine can cost hundreds of millions in lost revenue. To a board of directors, that looks like a self-inflicted wound. They see a system that's worked for 30 years and decide to run to fail. And from a cybersecurity risk management perspective, it's hard to argue with that logic. In a world of infinite resources, we'd replace everything tomorrow. But in the real world, risk management isn't about being invincible, it's about deciding which risks you can live with. If I'm sitting in that boardroom, I can see why they choose the status quo. When the cost of the fix is a guaranteed $200 million loss in downtime, and the threat being the chance of a hack, most businesses will gamble every single time. The problem is that this isn't just a business risk anymore. When these companies decide to run to fail to protect their quarterly earnings, they aren't just gambling with their own money. They're gambling with the stability of the grid, the water, and the infrastructure that we all rely on. The math makes sense for a business, but for a society, the math is terrifying. But the world isn't just sitting still and waiting for the lights to go out. Over the last few years, we've seen a massive shift in how governments and engineers approach this problem. In the UK, the government has stepped in with the NIS regulations, a set of laws that have legally forced operators of essential services like water, energy and transport to meet a higher bar of cybersecurity. For the first time, running to fail is no longer an option for a legal business strategy. If your infrastructure is deemed a risk to national security, the fines can reach into the tens of millions. There is also a push from the National Cybersecurity Centre. They've moved away from the idea of the air gap and towards something called active cyber defence. They aren't just building walls, they are hunting for threats inside the networks in real time. They say that modern OT environments are too interconnected for true isolation, and that organisations must assume compromise inside the network, not just defend the perimeter. On the more technical side, the Frankenstein's monster problem is finally being tackled with digital twins. Instead of guessing what an update will do and what the network diagram is of an OT system, engineers create a perfect virtual replica of an entire plant. They can launch 1,000 simulated cyber attacks against the virtual version to see exactly where the core logic program breaks down, all without ever touching the real-world machinery. It allows us to patch the past without risking the present. We're also seeing a rise of AI-driven anomaly detection. Since OT systems are repetitive, a pump usually does the same thing 24 hours a day. AI is incredibly good at spotting when something looks off. If a valve opens 3 milliseconds too late, the system flags it before a human operator even notices. It's a transition from being reactive to being predictive, and it can hopefully help cybersecurity professionals find that OT malware before people's lights switch off. From a risk management point of view, these advancements are a massive leap forward. We're finally moving from the cowboy era of connecting old machines to the internet into a structured professional defense. But the race isn't over. While we are building better shields, state-sponsored actors are building better weapons. The invisible technology that runs our world was never meant to be a battlefield. But now that it is, we have to decide what's more expensive. The cost of upgrading our foundations, or the cost of watching them fall. Because at the end of the day, The most dangerous threats are the ones we refuse to see.